Okay, today we're going to talk about training and testing our classifier. If you remember from before, when we build a classifier, we need to return it to the user together with some notion of how good this classifier is and how well it will work on data that it hasn't seen before. So we want our classifier to generalize. This is the word. We want it to generalize to unseen data. But in order to do that, we need to make sure that we give the user a reasonable estimate of how good our classifier is. So what we're going to see here is training of a classifier. And we're going to talk about the postulate in pattern recognition and machine learning, which is the more data we have, the better our classifier will be. So we are striving for big data, and when we have big data, we don't know what to do with it, but still, big data is large data sets are what we want in order to build a good classifier. And it makes sense. If you see more of a something, or you practice more of a something, then of course you will learn more. Then we're going to talk about a very important issue, which is overfitting and generalization. Overfitting will be when our classifier manages to score very well on the training data, but we cannot guarantee what happens on the testing data. And then we're going to see training and testing protocols, which are about using the data in order to figure out how good our classifier will be on unseen data. So remember this picture from before. Our classifier operates by taking the features and outputting a class label. And we need a data set to train our classifier before we deploy it. And we need this data set also to figure out how good our classifier is. So we train something like our black box, our brain machine, to get the class label. The bigger, the better. Bigger is better. The more data we have, the better the classifier will be. So let me give you an example. If you look at this data set, hopefully you can make out that there are two colors. One is red, one is black. Can you see a pattern in the data? Can you think of a way to distinguish between the red and the black in some general way, like one is an ellipse, the other is everything else? I don't think that there is a pattern that you can see. Now, how about I generate more data from the same distribution? Still, I don't see a pattern in that. I don't even see a pattern in that. Maybe more in the center, we have got more reds and some more blacks on the side, but I can't see a pattern appearing either. And look, my data set increases and increases, and the more data I have got, the better I can judge what classifier I can use and how I can discriminate between the classes. So this one looks like more of a pattern. First of all, we can see that data is not scattered all over the place there in a kind of a circle. But apart from that, the pattern between the red and the black, that pattern is not particularly clear. Here, maybe you can start noticing some kind of pattern, but in order to see what's happening, we need a lot and lots and lots of data. Now you can see that there is two spirals intertwined, and this is what our data set looks like. So this example is only to show you that sometimes even in small sample spaces, like two-dimensional spaces, we need a lot of data in order to figure out what our classifier should be doing. And this is where we define overfitting on this slide. So look at the data set, top left corner is the plot of the data. This is what I have got. This is my training data. This is all I have to train my classifier. So I can train a classifier by just drawing classification regions as you see in the plot in top right. And those regions, remember classifier and regions, they're the same thing. If you have the regions, you have the classifier, because the classifier, as we know, is some algorithm that will give a label to any point in this data space, wherever the point lands. So I've got little islands there that will be the black class here and here. And I've got some peculiar shaped regions. But this classifier that I trained by hand, drawing the line, recognizes my training data 100% completely. However, what happened here is that I might have learned, with my classifier, I might have learned all the noise in the data. And I have memorized the noise. And then when I deploy this classifier to unseen data, it will start classifying the noise wrongly. This is where we have got overfitting. Overfitting means that we fit the data that we have without a thought of what happens next. Overfitting would be if I give you the exam questions now and train you on the exam questions and then examine you on the exam questions, and that will be what happens. You will score 100% on the exam. But the idea is that I want you to generalize, to learn, and that overfitting is not a good idea. Memorizing everything is not a good idea, because things that will come further come from understanding, not from memorizing that much. Memorizing is good, don't get me wrong. And the way things are going, the exams this year, I think, are going to be like standard exams. At least this is the plan now, closed book exams, which means that I may ask you questions to reflect on things that you have seen in the slides, or just replicate them, or not exactly replicate, but explain in your own words. So memorizing in this case will be a good strategy. Anyway, pardon me, I'm healthy. Not even sore. So the optimal boundary for this data set is what you see there on the bottom left. This means that if I have got data coming from the same distribution with those class labels that this distribution implies, I cannot guarantee better accuracy of the classifier better than this classifier. No other classifier will give me as accurate solution as this classifier when I generate more and more data. Think of some of the data that fall in the wrong region as not true representatives of their class. This may happen. Overlapping regions means that there are points from the wrong class in the region. And this happens because our classifier is not perfect. We don't know everything about this data. We know only those features, and in the space of these features, these two features, classes are overlapping. Obviously, there is an entity out there that knows exactly what the class labels are, because this is how the data has been generated. But in that two-dimensional space, our classes are overlapping. Nonetheless, the optimal classifier is that linear classifier that you see there. So how does this happen, the overtraining and the overfitting? Here is an example. Suppose that you are training a neural network, and on the x-axis, I have got something that we can call, let's say, epoch. Epoch is when you take your training data and you submit it to the training algorithm, and the training algorithm does some learning. And then you take the data, shuffle it, submit it again, and the training algorithm learns a little bit more. And again, you take the data, shuffle it again, give it to the training algorithm, and every presentation of the data to the training algorithm is called an epoch. So suppose that this is epochs going on, and you can see that the training error in the top plot goes down and down and down as we expect. And the best training error is at epoch 19, and I can say, right, I'll stop the training here because I have reached enough low enough error, and I will return that classifier to the user. But look what happens if I simultaneously check the error on some unseen data set. That is the data set, the data that will come in the future, unseen. I've got the testing error going down, and notice that these two are not to scale. The testing error comes up to 0.21, and the training error is much, much lower. So this training error that we are going to return to the user has really nothing to do with the actual error that our classifier will make on unseen data. So what use is this classifier to the user? Very, very misleading. The classifier may diagnose people incorrectly, and that will be a total disaster. So what happens is that first the neural network learns the general idea of the discrimination between the classes up to there. From this point onwards, it starts memorizing the noise. So this is where overfitting comes, and this is why the testing error goes up. Because by memorizing the noise in the training data, that generalization is lost. The classifier starts behaving badly. So this is where overtraining and overfitting occurs. Now we're going to talk about training and testing protocols, which is one of the very important core concepts in machine learning. How can we measure the accuracy of the classifier so that we have got a reasonable estimate? The first and the very wrong method is resubstitution. Resubstitution, long word, difficult word. Resubstitution means that we use the same data for training and testing. So training will be blue, testing will be yellow, and we see what we have. Z is our data set. We use it for training and we use it for testing. One of my favorite questions, I have a lot of favorite questions, on closed book exam on this module is describe training and testing protocols that you have studied. So I pretty much want you to reproduce this slide and with a little bit of text to tell me that you understand what these things mean. So in this method, resubstitution method, so this is why it is good to learn that long word. The resubstitution method means that we use the same data to train and to test the classifier. Well, we saw just one slide before that this is not a good idea because we may be misleading our user. Our classifier may be learning the noise, and then when you return that estimate, our user will say, yeah, great. However, having said that, if we have a data set which has only few features and then lots and lots and lots of objects, like a tall data set, remember that that slide from second lecture, I think, then we may trust this estimate. This estimate may not be that wrong. So depending on the data set, this actually, the resubstitution method could be not such a bad idea, but that only happens in small proportion of cases. So in general, resubstitution method is not very useful. The probability of error that we estimate here is sometimes called the apparent error rate. So if you meet this phrase somewhere, this is resubstitution error. This method is also important for you because I will ask you in assignments and exam possibly to calculate resubstitution error of some classifier, which means train the classifier on the data I have given you and test the classifier on the same data, calculate accuracy or error. Holdout method is the next best thing. What can we do instead of using the same data for training and testing? Simple, we can split it into two. we can split it into two parts randomly, one part for training, another part for testing. So our testing data is not seen during the training. So our testing data will be a good measure of how good our classifier is. Recall that curve that we had before, and we had a testing data which showed us where we should have stopped with the training. Okay, can you think of a reason why this method is not very good either? It's very subtle and difficult to just pull out of the air, but can you think of a reason? Why would this error, this estimate, be not particularly good either? Correct, because we are only training on half of the data. So the classifier that we are estimating, that we are evaluating, is actually not the classifier that we will return. We will return a classifier trained on the whole data set, because the bigger the data, the better. So the classifier that we train for half of the data will not be that good. So the error that we calculate will be actually a pessimistic estimate. Our classifier in reality, when we return it, will be better than that. So in a way, that second method is a bit of an insurance. If we return the holdout error, the user can expect that the classifier that we return will be perhaps slightly better, but a little bit better. So that's not a very accurate estimate either, and we don't want to lose half of the data to if we can use all the data to train a good classifier. So this also could be misleading. But the good thing is that we are testing on unseen data. And then, since we have that drawback and holdout method that we are training on a very small part of the data, people came up with another method. It is called the data shuffle method. So it is split into two and repeat. Typically, we split the data, but not in half. We split the data into 90% for training and 10% for testing. So we have got a larger training data. And then on the testing data, we calculate the error. We repeat that procedure by shuffling, splitting, and training and testing. We repeat this, let's say, 100 times, and then we average the testing errors that we have from each split. And this is how we get to one single estimate of the error. So that's data shuffle, but the most important method for training and testing is cross-validation. So if you know anything about machine learning after you finish that module, that should be cross-validation. That is something, overfitting and cross-validation. Cross-validation is the protocol that everybody uses. Every paper, research paper, or scientific paper that you open about machine learning, there will be guaranteed some cross-validation testing of the classifier. So what is cross-validation? It is similar to the data shuffle where you split, train, and test, but this time we are not taking the data, shuffling and splitting randomly to do that evaluation in one of the passes in the experiment. This time we are splitting the whole data into k folds. In this example, it is 3. K is 3. So threefold cross-validation means split the data into 3 equal parts, use 2 parts for training and 1 part for testing. So k minus 1 parts are put together as our training data, and the last part is used for testing. And then we put back the one fold that we took out, take out another fold, and do the same training and testing. And then average the testing result, average the testing error, or if you are measuring accuracy, average the testing accuracy. And that is what we return to our user. So hopefully cross-validation is more accurate and more close to the true error of the classifier compared to alternative training and testing methods. So the good thing is that we are training on non-intersecting data sets. So each of the points in the data set is participating in the testing only once. Because the first fold, those will be the data left out. Testing goes on the yellow. In the second fold, second time, this will be the data for testing, and this will be the data for testing. So these are different parts of the data. Not like in the previous example where we have data shuffle, where the testing parts are overlapping. We can have the same object used for testing in multiple of those experiments. We test on unseen data as with the other methods, holdout and data shuffle, and the data set for testing has got the same size as the training data because every object will be used for testing once. The bad thing is that if we have 10-fold cross-validation on a relatively small data set in terms of number of objects, then our yellow parts are going to be small, and we calculate the error rate on these yellow parts. And if we calculate the error rate on these parts, the error rates could be varying a lot, because those objects that are left out, they could be anywhere in the space. So our error is going to vary a lot. So that's a problem with cross-validation, and this is why people normally use 10 times 10-fold cross-validation, which means do cross-validation by splitting the data into 10 parts. So cross-validation that way, then put the data back together, do another split into 10, do another cross-validation, and then average all the testing results. That is considered to be the most accurate estimate. And finally, a method which is important when we have got a small data set, only few objects, is leave one out. It does what it says on the tin. We leave one object out for our testing. Everything else is the training. So it is a cross-validation, same thing, only we have got n-fold cross-validation because we split the data into n parts, one object at a time. So what happens is we train a classifier on nearly the whole data set, but one object. So we have got the classifier that we do want to evaluate. Then we test the classifier on that single object. Imagine that we want to calculate the accuracy. So this one object will either be correctly labeled by the classifier that we train, which means 100% accuracy on this fold, or it could be mislabeled, which means 0% accuracy on this fold. So for every fold, I will have either 100% accuracy or 0% accuracy, or if I don't use percentage, use proportion, I will have 0 or 1. And when I average across all the n folds, I will get my estimate of the accuracy of the classifier. So the good thing about that is that we are training our classifier on the maximum possible data set, and still we are able to evaluate its accuracy. So that's the good thing about leave one out. Leave one out is useful when our data set is not particularly big. If we have a big data set, which means lots and lots of objects with their labels, then we don't need to bother that much with leave one out or cross-validation. If we have 30 million images and they're all annotated, then we can use just called out. That will be good, or even resubstitution in some cases will be good, but holdout is the one that should be used in general. If we have a big data set and we want to be really good and precise, what we can do is take the training part of the data and split that training part into two. So this is why they're blue, both of them. One will be for training the classifier and another will be for validation. So these both parts of the data are seen during the training. We build the classifier on this dark blue, and then we evaluate it, test it on the validation, and this will give us an idea of what happens on completely unseen data. Then we have got the other part of the data set as testing. So the training and validation tune the classifier. We pick the best model according to this couple of subsets. And after we do that, after we have got our classifier trained according to our blue part, we test it on unseen data, and that should be the most precise estimate that you return to your user. The thing is that the more data we have, the better the classifier will be. That is true. But in some cases, it turns out that it is enough for this classifier model to have a certain amount of data, and additional data are not going to improve on the model, even marginally. Just the model is trained well enough. And this is when you have got a simple model and a large data set, then we can safely use holdout approach. If, however, we have got a complicated model, then we need a more sophisticated and smaller data set, more sophisticated training and testing protocol. Okay. So the validation here is to prevent overfitting. That's the idea, and that's one way of doing so. So let me give you an example. This is the two spirals data that we saw before, and I can generate the data so that there is no noise whatsoever. We have got the same size of step in the generation process, and you can see the ideal data with no noise there. If we allow the step to be random, you can see that the two spirals are still visible. So this is top right, ideal data, noisy step. And then if we also allow the points to move away from the spiral, just oscillate a little bit randomly, we get the data set that we saw before. And I have got examples of small data set, 100 objects, medium data set, about 1,000 objects, and large data set, which is 15,000 objects. And again, as we saw before, in order to see the pattern in this particular data, we need the large data set. Otherwise, our classifier will get confused. So here is my training data on the left. I don't know, but this may be 200 objects. I don't remember. I should have written down the count. Never mind. So this is my training data on the left. This is all my classifier will see. My classifier will try to learn the pattern only based on this data. So chances are that the classifier will not learn anything, and our accuracy is going to be 50%, random. Same chance for both classes. Well, it turns out that the classifier can learn a little bit better than random. I'm going to use the data set on the right as my true real-life data set that will come after I deploy the classifier. Of course, I cannot generate all possible points there because there are infinitely many. If I have got random oscillations, small random oscillations about the curves, the spirals, but I take a large enough data set to be able to judge what happens in real life if I test my classifier on that real life data set. So this is our true data set, and our true error will be calculated on that, or accuracy. So here is an example of what happens, classification regions, if I apply the so-called decision tree classifier. You're going to see that decision tree classifier, how it operates and what happens there later on in the module. But for now, all you need to know is that the regions that the classifier produces are separated from one another with lines that are parallel to the x and the y coordinate axis. So if we have three-dimensional space, the regions will be planes that are parallel to the planes xy, xz, yz, those, the floor and the walls. So you can see that the regions that the classifier identifies from the training data, this is not the training data, this is actually testing data. I haven't plotted the training data here. I just use the training data to get those regions. So the regions are nowhere near what the two spirals look like. So this classifier is not overly successful in classifying the two spirals data, and you can see why, because the regions that we are looking for, they can hardly be approximated very easily with lines that are parallel to the coordinate axis. It could be, if we have a lot of data, our decision tree classifier is going to do that. But if we have a small data set, as we had in this example, this is what we get as the regions. So if I train my classifier on my training data, I get 84% accuracy, which means that I train my classifier on this data set on the left, I test it, and I get 84% accuracy. But you can see that this is nowhere near correct for the data set that we have. So if I take the real data, that was the big data on the previous slide, and I have replotted it here with smaller points so you can see where the real data is. The true accuracy is 57%, which is not bad. Our classifier learned something. It is not 50%, it is 57%. And if we're talking about human lives, let's say, these 7% are a huge improvement compared to just tossing a coin. So how can we estimate the error of this classifier? And the error should be something that is similar to a true. This is what we want to guess. But we only have the training data. We don't have the testing data. We can't use it to just measure the accuracy. We only have the training data, and using this training data and our training testing protocols, we want to figure out what happens. Hold out. Half of the data is used for training, another half for testing. And look what happens. The true accuracy that we are after is 57%. If I use holdout, I train my classifier, I test my classifier on unseen half of the data, and I get 53%. Remember, that is a slightly pessimistic estimate because we are training our classifier on half of the data and our classifier is not as good. But it is much better than telling the user that their classifier is 85% accurate. And this is what happens with cross-validation. What you see here in these 10 plots are the classification regions that were produced by the respective classifier of the fold. So I removed 10% of the data, I trained the classifier on remaining 90%, and I get this region. And I remove another fold, I get this region. pretty cool, like abstract art, aren't they? So you can see that the accuracies at in the different folds are very different. And these are the accuracies that I calculate on the testing part of my data. And you can see that here, for example, the 10% of the data that was left out was positioned in such a good way that the estimate of accuracy on this small data set was 73%. But if I run that on the true data, the accuracy is going to be much, much less. It doesn't matter, by the way. What matters is that I have got those different accuracies calculated for the folds, then I average them and I get 57%. And that's pretty close to what we want to estimate. If I apply leave one out, I get 55% accuracy, which is again close to the truth. So it seems that our winner is tenfold cross-validation, which gives us a good estimate of what we can expect from this classifier if it is deployed in real life. So again, all these calculations were done only on the training data, and then we can see that we have got a good match if we use the training and testing protocol that is cross-validation. Okay, so question to you now. I have got a data set and I've got two splits, split 1 and split 2 for the holdout method. Which one shall I use? Split 1 or split 2? This is for the holdout method. One is training, one is testing. Come on. 2. Yeah, that's correct. Because look what happens if I train my data on the training part in split 1, my classifier will know nothing about the testing part. So whatever I use, whatever classifier learns here, will be no use on the testing data. So that's not a good idea. So this is why we shuffle the data, split them randomly, and this is how we get our training and testing. Okay, question 2. How many calculations of the testing error do you need to carry out if you run 5 times tenfold cross-validation on a data set with that many objects, that many classes, and that many features? So this is a trick question, because the number of objects, the number of classes, and the number of features don't matter at all. Okay, I'll leave you to think about that. Then we have got a data set in 1 dimension. I have kindly ordered the data according to the value of X. We have just one feature. I have got class labels. So each of these points with one feature has got a class label. So suppose that you are training a classifier and you're training the classifier in the following way. Take all the objects that are from class 1 and find the mean, the average. That will be your representation of class 1. Take all the objects that are from class 2, find the average. This is your representation of class 2. Then you have got 2 points, class 1, class 2 representatives, the mean. And then split in the middle by adding them up and dividing by 2. This will be your threshold T. Then use this threshold to create a classifier. Everybody on one side, on the side of the mean of class 1 will be class 1, and everybody on the side of mean of class 2 will be class 2. So The two tasks are apply the resubstitution protocol and evaluate the classification error of D, which means use all the data as you see it in the table, train your classifier by finding that threshold, reclassify the data, so for every data point, see whether it is correctly or wrongly placed there, and calculate the error. Then do the same with leave one out, which means take one object at a time, build a classifier on the rest, label that one object, and then put it back, take another object out, retrain the classifier